Happy New Year, everyone. As you noticed, I know many of you are returners and started with us at the very beginning of this series, so welcome back. And for those of you that are new to this series, I just want to remind everyone that we have videos from every previous talk if you want to go and visit and learn about the content that was presented last semester, by all means. I will mention too, our new Science Cafe brochure is out. Unfortunately, we were delayed with a pretty severe accident at Tangerine and Oracle, so you noticed our table wasn't set up as we usually have it set up in advance of you arriving, but everything is set up and ready for you if you didn't have a chance to pick up some of our materials. So the new Science Cafe brochure for spring 2018, which lists all 4 venues. Obviously, Saddlebrook Science Cafe is one, Tumamock Hill, way down in town, obviously next to A Mountain, 100-year-old facility. Our Magpies downtown Science Cafe, as well as the Borderlands Brewing Cafe. So all the talks, titles, series are listed in there. Of course, you can always visit our College of Science website, and we also have the link here. So you can read about all of the series. And how many of you are familiar with the College of Science lecture series by a show of hands? Excellent. I know it's a bit of a ways to travel down there. For those of you that do, then get to enjoy it in person. It is a unique and wonderful experience to be in that community learning about science. The beauty too is that it's simulcast. So we partner with Arizona Public Media. And so it is simulcast, so you can watch from the comfort of your own home. We've even heard tell that a lot of people in Saddlebrook make a party out of it and gather and have folks together in a home to watch one of the lecture series talks. We do have that brochure, all the talks, titles, link to look at all of that as well and get instructions on how to receive that in your home. All right. So as you may be familiar, this series is called Earth's Core to the Clouds. And again, it's one of 4 other venues. There is talks in the works. How many of you visited Tucson Botanical Gardens? Hopefully, okay, great. Nice show of hands. Wonderful jewel in the middle of town. We're looking to offer a 5th series at Tucson Botanical Gardens as well. So more news will be coming. How many have visited Science City as part of the Tucson Festival of Books? Great. Okay, maybe we'll get more of you. In addition to, we have 80 booths of hands-on activities and 5 themed tents like Science of Tomorrow, Science of You, Science of the Natural World. We also have a Science Cafe tent. So similar to tonight and the series that we offer year-round, we'll have a lineup of different speakers from different disciplines both days, all day. So by all means, you want to check that out on the website for Science City. And of course, we'll have 2 full days of nationally or internationally recognized science authors and panels on our main stage as well. And those of you that haven't had a chance yet to visit the Mirror Lab, there are free tours all day, both days, and a plethora of other open houses and free tours. So you don't want to miss Science City. And actually, this is the 10th annual Tucson Festival of Books. Woohoo! And we convinced them that the theme should be the power of 10. So that's the theme within our Science City and the Science Cafe as well. So check it out. And so just to remind everyone the format that we follow, in a moment here, I'll introduce our fabulous faculty member who will be speaking on his research related to the theme. We'll let him give his presentation. I understand it's pretty interactive, so we do encourage your interaction with him. And then following that, we'll take question and answer, and we'll just be roaming with microphones. Do me a favor and take the microphone, pose your question, hand it back to myself or Samantha so we can move on and have someone else get to ask a question. We'll moderate that for a period of time. And then for those of you that didn't get to ask your burning question, Jay has made himself available afterwards. So you can gather at the front here and he'll have some one-on-one conversations for a period of time. And then we'll rescue him and send him back to Tucson. Just kidding. Yeah. Actually, we get great feedback from the faculty that come and speak at Saddlebrook. Your fabulous audience. It's a bit of a trip, but it's made worthwhile by your engagement and interest in the topic. So that really was just a tease. We do also, in addition to all of the College of Science materials, just to remind you that there are wonderful outreach facilities and research facilities open to the public. the Science Cafe series and the lecture series, but also the Department of Geosciences, if you didn't know, we're always in the top 3 in the country for physical sciences, and geosciences puts us literally on the map. So there's information about the department out there, how you can get involved or how you can support geosciences. So if this is your passion or interest, by all means, take those materials. All right, without further ado, we do have evaluations outside as well. Probably our primary goal with having the evaluations is so we can give our speakers your feedback, which is really powerful for scientists coming into the public so that we can encourage them to continue giving public talks. And then it's a big part of their professional development, obviously. And then also we learn from you the areas you're interested in us bringing out to Saddlebrook. So by all means, give us your feedback on that. And if you elect to put your email address there, we will send you announcements about upcoming events like Science Cafe here, lecture series. We never ask for money or anything like that. So make sure your email address is written clearly so you can get those announcements as you like. Okay, so tonight's talk is the Anthropocene, the human footprint, and it's going to be presented by Dr. Quade, who is a professor of geosciences. He received his bachelor's from the University of New Mexico, his master's at U of A, and a PhD at the University of Utah, and did some postdoc work in Australia. Jay's research focuses on reconstructing environments in the past, asking what did our world look like during various geologic periods. In a typical year, he spends 3 months in a tent and a sleeping bag, part of why he loves his job. And for him, geology is a family affair. He's a 3rd-generation geologist, and he carries his grandfather's compass and his father's hand lens with him for his field work. And tonight, Jay is going to discuss where in time does the human footprint begin? And how will our world, our footprint, be viewed and interpreted by future inhabitants of the planet? So without further ado, Jay, the floor is yours.
How's the sound? Is that okay? Is that all right? Just like that? Okay. Well, good evening, everybody, and Happy New Year. It's a delight to be here. And it's a particular pleasure to talk on this topic because it has to do with time and the issue of the organization of time and what we call various time periods. And to geologists, that's a really critical question. You can ask my wife. When I wake up in the morning, I rarely remember to comb my hair. Sometimes I get my underwear on backwards, and all kinds of sort of crazy scientist things that I do. I'm afraid I fit the stereotype. But on the issue of time, I'm very strict. And geologists in general are that way. How to designate time, how to organize it, because it's the entire framework of our world. So let's have the first slide, because there's a big and interesting debate going on right now about this question of what time period we live in. Formally speaking, we live in what's referred to as the Holocene period. That's the official designation. We've been in the Holocene epoch for about 10,000 years. And the big question is whether we should change it, whether we should name the current time period we're living in actually after ourselves. And so it's been proposed that that geologists, I think informally, a lot of people accept this idea, but the question is getting formal acceptance to it. And the issue of defining time for geologists is very tightly choreographed. There's a bunch of rules involved there. And so far, geologists can't agree on an official start for the Anthropocene, and so officially we're not living in it yet. But unofficially, believe me, we are. And I think it's coming. But the big question is that I think geologists are wrestling with, and it's actually, I think you'll enjoy this. It's a really interesting question. When does the human footprint actually begin? When do we formally define that start? We've had so much impact on the surface of the planet, and that impact is increasing exponentially. Where on that exponential curve do you mark it? Where's the start, the official start? There's also this other question of how it's all going to end. Are we going to be around for a short period of time or a long period of time? And boy, I sometimes wonder. I don't know. But actually, I don't think it really matters. If we went up unfortunately, went up in a nuclear plume tomorrow, we've had such a profound impact already that there's a question in my mind that we deserve to have our own geologic period, even if it's short, and that, and this is going to be the punchline at the end of my talk, that there's no question when it comes to tourism in the future, we're going to be a key attraction, our archaeological layer. People are going to think about us and study us and probe it and have professorships and departments and universities about it, trying to understand our world. Our impact is profound. So that's the argument. That's basically what I want to talk about in a nutshell. To get us warmed up, I actually want to go to a film clip from, here it comes, 1968, Charlton Heston, Planet of the Apes. I want to show you the last 2 minutes here. There's a couple of key things that I really like about the film. So let's see if we can run it here. Just 2 minutes. Almost certainly everybody's seen this film, right? I was 13 years old when I saw it. It had a profound impact on me. Here it comes.
Oh my God. I'm home. All the time. Finally, really did it. You maniacs! You blew it up! Oh, damn you! God damn you all to hell!
Yeah, go ahead. Next slide. So hold it there. Okay, 2 reasons I wanted to show that clip. Number one is Charlton Heston should have gotten a prize for overacting. Huh? Oh man, they don't make them like that anymore. What a classic. Although probably for that period, the award for overacting should have gone to William Shatner as Captain Kirk. But there's something about that era and just the way they did all that. The other implication to this is actually a lot more serious. For once, Hollywood, I don't think, got it that far wrong. They didn't exaggerate things. This ending, I think actually sort of things like this are going to happen. Not necessarily people are going to ride up on a horse like this with a beautiful woman and you know, there's the Statue of Liberty, but future sentient creatures, and I don't know who they are, maybe our descendants, maybe some other separate emergence of intelligent life, they're going to look upon our archaeological record and our remains with profound curiosity. And so my basic feeling is that the film from that point of view got it right, and that's why I think the film for me really impacted me at the time, because it just really had a ring of truth. I think things like this are going to happen because we are leaving such a conspicuous archaeological layer behind, and as I'll point out in the end here, I think it's going to be a major tourist attraction. Now, geologic time periods. Let me turn to a little bit of the technical aspect, or the technical issue of defining geologic time periods, because this is a serious matter for geologists. Typically, they start and end with major extinctions. They're based on fossil evidence. They're based on the sudden appearance or disappearance of major fossil assemblages. And there's several really well-known ones in the geologic record. I don't have a pointer here, but I think I can still point it out. For example, the Permo-Triassic extinctions there in the middle, and the KT extinctions over off on the left. The KT extinction is referring to the Cretaceous tertiary extinctions. And most of the major geologic time periods are defined in that way. And so we have to think about the Anthropocene in this context, about how we might be, and in fact this is happening, how we're inducing major extinctions. And to the extent that's one of the criteria geologists use, it actually is, we're actually doing it. In fact, we're in the midst of, I think we're ranked number 5 in terms of major extinction event. The biggest one is the PT extinction there, which is 250 million years ago. That's the mother of all extinctions, right here at 250. I'm not going to talk about that one tonight, but it's a fascinating event. It's involved an incredible level of die-off, particularly in the ocean. Something like 95% of all marine organisms died off in that extinction. But I won't talk about it because we actually don't have a good explanation for it right now. There's a lot of debate, but nobody knows for sure why that one happened. The KT extinction, on the other hand, I do want to talk about that one because it's so well known. It's a lesser extinction, but it's well known because it was so dramatic. And I want to hold it up as an example of what geologists regard as a geologically conspicuous time transition or extinction. And at the end of the day, actually point out that despite the fact it was dramatic, it is nothing compared to what we are doing. Nothing. It's really a minor event. So we're going to travel around the world and have a look at what the KT extinction actually looks like. And when you think about it and realize that, that gets geologists excited, imagine what the archaeology of our layer, what that's going to look like to future geologists. Okay, so let's focus on the KT extinction. Cretaceous tertiary, it's famous. So somebody in the audience, tell me about the KT extinction. What happened? Dinosaurs, that's the usual response, and that's actually absolutely correct. Dinosaurs were just one of the major animal groups that was taken out by the, and it's actually only, I gotta qualify that, it's only the non-avian dinosaurs that were taken out. The avian ones survived, right? Those are birds. But the avian branch of the dinosaur family was taken out, and is pretty solid evidence that this event had to do with a meteor or an asteroid impact, and it occurred. Now, this is a map of 70 million years ago, and the world was a little different. Back then, there were no ice sheets, and if you melt the ice sheets and it runs into the ocean, you raise sea level, and so that's why things look a little bit different here. But the meteor strike actually occurred in northern Yucatan, and you can see North America up there, sort of Tucson in the Cretaceous under the clouds, and just east of Tucson, there was a giant shallow seaway that ran up through Central America, Central North America, which with a drop in sea level is no longer the situation. But anyway, it was a greenhouse world. It was a wetter world, and this meteor strike, which was has been very precisely dated at 65.5 million years ago, occurred in northern Yucatan. All right, excuse me. Next slide. So for geologists, it's not boring. Most geologic transitions in the record are incredibly boring, even to geologists. They're so subtle. They're these paleontologic changes, and it takes a specialist to identify it and have it pointed out to you. That's not so much true with the KT boundary. It actually is physically pretty visible in a lot of places, although not everywhere. It was actually discovered and described by the Alvarez father and son team back in the 80s, and they were the first ones to suggest that actually the extinction of the dinosaurs and many other animal groups was related to a meteor impact. They were dismissed as crackpots at the time, but a lot of what turns out to be good scientific ideas, that's the way it goes, and this was one of them. It's gradually been accepted. I think there's very compelling evidence for the basic argument that it was indeed a meteor impact. I'll show you some of the evidence for it. But, you know, at the end of the day, it's kind of a, I don't know, in most places you go see the Cretaceous tertiary boundary and it's kind of a nothing burger, you know? I don't know how else to describe it. This is the boundary in Gubbio, Italy. And Walter Alvarez has his hand on it. It's marked by that dark sort of coal layer right there. but so what? You know, it's just not that spectacular, and that's the case in most locations across the Earth. It's pretty subtle, unless you're near Yucatan, and then it's a lot more conspicuous. But this is one of my points: is that this is pretty subtle. What we're going to leave behind is not going to be subtle. It's going to be a Ford truck sticking out of the outcrop, you know, and people are going to know that something really unusual occurred during that time period. So, so next slide. How do we know that actually? I want to walk you through it because it's the anatomy of probably the most famous geologic boundary. But at the end of the day, most parts of the planet, it's not that conspicuous. But the way the Alvarez has picked up on it is there were two clues. One is that they found anomalous levels of this very rare element, iridium, which is common in meteorites, but it's not common on Earth. And there was an iridium anomaly. There was lots of iridium in that layer I just showed you, and they were puzzled by that. There was no known terrestrial way to do that, and so they really began to look at extraterrestrial sources, and the most obvious possibility was a meteorite. And at the end of the day, I think they were right. Another smoking gun was the presence of shock quartz in an area particularly around the Gulf of Mexico. A lot of geologists were looking at sand grains from that boundary layer, and they noticed that now normal quartz on the left there just has a sort of normal color pattern, but on the right you'll notice there's a bunch of stress or shock patterns in the quartz. And that's from the meteorite hitting marine sediments and just high pressure metamorphism just shocking the grains. And the Alvarezes noticed that. And so they sort of put two and two together and they said, boy, this looks like an asteroid. Now they didn't know at the time that, next slide, this was only subsequently discovered by petroleum geologists looking for oil in Mexico, that they detected using gravity images over on the right there, the presence of some kind of large circular feature. And when they drilled down in it, they found a lot of evidence of melted rock from impact by some kind of dramatic heating event that melted a lot of rock. And vaporized sulfates and carbonates, that's important because those become gases then in the atmosphere that modified the climate. And we now know that what these petroleum geologists identified was the actual impact, because geologists have been able to date it, and it dates exactly to that time when the dinosaurs go extinct, and a lot of other taxa. Just for scale, the scale of the actual crater itself is about 200 kilometers. That's about Tucson to Phoenix. So crater to crater, you climb in a car. If you drive across the crater, you'd reach the other side when you got to Phoenix. So it was a large feature. The asteroid itself was about the size of, like, the interior of Tucson from about downtown over to Kolb. That was about the size of it. So that's a major impactor. Things like that fortunately don't strike the Earth very often. When they do, they cause major extinctions, as in the case of this one. But they probably come along every 50 to 100 million years. Some of them strike in the open ocean and are a lot less effective in changing climate. This one happened to strike sort of half on continent and half on ocean. And because of the vaporization of the sulfates and carbonates, it had some really major climate effects. Now, the dinosaurs were not killed by this impactor. This impactor was actually a fairly local event. It was the consequences that followed on from that killed off so many of these various animal groups. So next slide. Before I talk about that impact, though, I just want to talk about this. I know the slide is a little busy, but I want to walk you through it. So it goes from purple to yellow, doesn't it? Left to right, purple being locations that are very proximal, and you'll notice the purple dots up on the map there that coincides with the Yucatan Peninsula. So right in and around the area where the asteroid struck, we have tens of meters of thicknesses of debris, just debris that was locally thrown up in the air and then landed. So that's pretty conspicuous, and obvious, but it's a local effect, confined to where those purple dots are. As you spread out in the red there to proximal, what you don't see all this impact breccia and debris. What you actually see is thick flood sands all around the fringes of the Gulf of Mexico. And Anybody want to guess what that is? Big sand layer. What's that sand layer doing there? It's quite marked in that time boundary. Let me give you the other hand. Next slide here. That's how the impactor came in, and the debris was sort of shunted northward. You see there over on the right how the asteroid came in at a low angle and then just blasted all this debris across North America. Well, that sand layer in red there, the proximal, that's a tsunami. So it was a giant tsunami from the impact site that spread out across the Gulf of Mexico and would have just inundated all the coastal areas. But again, that's fairly local as well. Here in Arizona, if you want to look at the KT boundary, it's more an intermediate type event there that's kind of an orange color. And there we're down to a sort of a centimeter scale layer of melted volcanic glass that fluttered down out of the atmosphere, and it's capped by a little coal layer. I'll show you a photo of it. And then even more distal to that, it's just a really fine layer in the deep ocean. The takeaway is in most of the planet, except around the Gulf of Mexico, it's just really not, it's nothing spectacular, this event. And yet, I mean, we were struck by this enormous asteroid and it had profound biotic effects. Next slide. Here's an example from Colorado what the KT boundary layer looks like. It's an ejecta layer there in white where the pocket knife is. And that ejecta is actually just very fine-grained rock that cooled the glass, and it's just fluttered down through the atmosphere. It got up into the stratosphere, and it just fluttered down a little layer, kind of like a Mount St. Helens sort of thing. And then it's followed by a soot and coal layer, which is partly a burn layer, but also mostly not from burning. It's from various sources of organic matter I'll probably talk about a little bit later. What's interesting is when you look at the pollen and the plant fossil evidence in the layer, what you see is lots of evidence of ferns and fungi. So the vegetation recovered very quickly. There's an example of ferns growing on a basalt flow in Hawaii. And in the immediate aftermath of this thing, broad swaths of forests were wiped out, but you had recovery in the form of lots of ferns and fungi. The fungi implying there was a lot of dead plants around to feed off of. But there it is. And you know, most people drive right past this. They wouldn't know what they were looking at. You need a specialist to take you out in that outcrop and point it out to you. Okay, next slide. So a series of consequences. The meteor strike itself was the earthquake and tsunami at a Richter scale 11. Richter scale 11. So what's the biggest known earthquake? Anybody know on the Richter scale? I heard some 8s and 9s. You're absolutely right. Not to underestimate this audience. You're right. So actually, I think there was a 9.5. The biggest one was in northern Chile. Now this is a Richter scale, so a scale. So every unit is a jump in dimension of 10, right? It's a log scale. So Richter scale 11 would be 10 to 100 times larger than the largest earthquake ever experienced in historic times. So it was a big earthquake, and it was a big tsunami associated with this thing. That was followed by, because of the heating of the atmosphere as this impactor came through the atmosphere, it basically created a heat shock wave. There's a lot of evidence for this, that it damaged plants and set off a fair number of wildfires. Okay, next as if that's not bad enough, and that would have killed a lot of animals, particularly in the immediate vicinity, the area around the Gulf of Mexico. Probably the big killer, though, strangely enough, was the cooling that resulted. Because imagine with this meteor strike, and we know we've injected all this debris and carbonate and sulfate up into the atmosphere, which are gases, and particularly sulfate is an icehouse gas. In other words, it prevents sunlight from coming in. Plus, you've injected all this soot into the atmosphere, and the general feeling is that the Earth, after this initial impact, went into an extended deep freeze, and that was the killer. Things that could survive are the things that could survive this cooling event, which extended over months to years. And so you'd imagine, it's not surprising, next slide, that if there's no sunlight, there's no photosynthesis. So there's a complete collapse in the food chain. There was not much to eat. It would be killed off all the primary producers and consumers. It would have favored things that could cope with a cold, creatures that could cope with a cold, and it could go a long time between meals. Those would be advantages. Probably describe some mammals. Mammals, they survive across this boundary. And in fact, they expanded the niches abandoned by dinosaurs. And it's the fact that they could cope with a cold, which was probably a really key thing. Anything living underground or in the deep ocean did much better than anything that was near the surface of the ocean or on land. So anything that nested down in the ground had a potential to make it. And birds made it probably that way. And remember, birds are dinosaurs, right? They're an avian form. So even some forms of the dinosaurs made it across the boundary. It's probably because of their capacity to nest in the subsurface, because it would have been too cold on the surface. So next slide. So the extinction patterns. Marine life is hardest hit. There's just some percentages of the major groups, including almost all marine reptiles. One of my favorites, if you anybody ever gone fossil hunting? And one of my favorites is looking for ammonites, which is that it's a relative of an octopus. It just lived in a shell. It's a Cretaceous cephalopod, and man, there were a lot of them around in the Cretaceous ocean. And I bet they were good eating too, but they got taken out. Boy, just unlimited squid, calamari. You could have all you wanted back in the Cretaceous. But they were completely wiped out by this. There was a deeper water form that's a near relative that survived. They're called nautiloids, and they survive today. They're a kind of relative of ammonites. They only survive because they live in the deeper ocean. Anything in the shallow ocean, forget it. Actually, the land, even though it's most famous for dinosaurs and the extinction of dinosaurs, land biota were not as hard hit. It is true that nothing above 25 kilograms survived. If you were big, you didn't make it. Close to 60% of all reptiles are taken out. But again, not all dinosaurs are killed off. And I'm reminded of that every morning. Next slide. When I look out to my bird feeder, it's not a hummingbird feeder. It's a dinosaur feeder, right? These are the descendants of the avian dinosaurs. It's hard to believe, huh? This guy's actually related to T-Rex, distantly, but he is. And so it's a good thing it's distant, though. Imagine you have a T-Rex in your backyard every morning. So relatively unaffected, higher plants, only 10% loss, and mammals are big winners because they're homeotherms. They can maintain their temperature. They cope to the cold, and so they made it through. Okay, next slide. So this is what I'm going to argue. This KT event, I mean, it's dramatic. It's Hollywood, right? This is, asteroids coming in and forest fires and soot in the stratosphere and deep freeze and extinction. But geologically speaking, we're also in the middle of a KT event. It's not as sudden as just an asteroid coming down out of the sky, but it is fairly geologically sudden. I mean, geologists deal with millions of years, and what we've done in just the last 100 years really almost looks like an asteroid event, almost looks like a KT event. So I would argue that we're about midway through a KT event, and in another 100 years, we're going to look like a full-on KT event in terms of mass extinctions and just general impact of the planet. But actually well beyond this impact, because as I said, we're going to leave our Ford trucks all over the place and more visible than an iridium anomaly. So what I mean by living in the middle of a KT event, population, billions of people. So let's see in the x-axis down here, that's time. We're going from the year 1800 up to 2000, and basically everything increases as you come up and as you come forward in time. Whether it's population, thousands, dams that have along rivers, urban population, motor vehicles, water use, paper consumption, telephones, fertilizer, McDonald's restaurants. I love that one, but that's for sure we're in a KT event if that's happening, and international tourism, and it goes on. Next slide. It gets worse. What we're doing to the atmosphere, an increase in carbon dioxide, in nitrates, and in methane. So that's the upper row there. Ozone depletion, increase in global temperature, frequency of flooding. So that's on land. In the ocean, major changes. And in the terrestrial realm, the one I would like to particularly highlight here is global biodiversity and species extinctions. So as I said, the way geologists define, the way we chiefly define transitions in geologic records is by looking at extinctions. And it's increasing exponentially. There's species disappearing almost weekly on the planet. And over the span of just a couple hundred years, we're going to look just like the KT event. And we did it. We're the asteroid. This is no exaggeration. I'm serious about this. This really, we don't realize it because people don't live that long, and we don't, relative to geologic time, a normal human lifetime, but things are moving so quickly relative to the way usually things work in the geologic record. We look sudden we're going in the future to geologists, we're going to look as sudden as the KT event. Okay, next slide. Okay, let's play a game here. All right, we're going to play a little Geo Jeopardy, and let's just pretend that you chose the Anthropocene for 500. So it's a little quiz here. It's a little test of, and I bet you guys are going to do really well. But let's click it to the next one here. This is what the game is. No, not that. Just hit return. Next slide. There you go. So here's the game. I've listed a series of dates here, and what I want all Jeopardy players here to do is to at least pick one of those dates out of the list, and try to identify in your mind what it probably represents. Now, these are dates that have been identified by various scholars as their sort of best guess as to when the Anthropocene started. And they're picking some major landmarks in human history. And so my question is, why choose these dates? Why 10,000? Why 1945? Why 1964? And so AD is just calendar years. BP is years before present. So 10,000 years ago, or the year 1945. So I'm going to give you 30 seconds. Let's click that thing up there, and I want you to just think about this. Pick one out, and I'm going to ask everybody to raise their hands and tell me what happened on one of those dates. So go ahead and click that. Just to get us in the mood. Don't laugh. I'm serious about this. All right, time's up. Let's see who the big winners are here. So let's start with 10,000 BP. Why would some scholar, some scientist come out with a paper basically saying, I think that the Anthropocene started 10,000 years ago? That's my call, because this is a big debate. Everybody's putting forward these suggestions. So what happened 10,000 years ago? Excellent. Very good. Okay. I don't know what the Jeopardy sound is for the correct answer. I can't remember. It's like beep or something. So next slide. Hit return. Agriculture. Agriculture and the population explosion. The beginning of the Neolithic in the Old World. Very good. So that's been suggested. Now, there's another rule of the game, at least from the standpoint of geologists. They like to choose boundaries that occur all at the same time across the planet. And so I'm going to push the audience on this one a little bit. What's the problem with 10,000 years ago from that perspective for the base of the Anthropocene? What's that? Yeah, it wasn't universal, right. In fact, agriculture arrives here in the Tucson Basin maybe 4,000 years ago, 3,000 years ago. So it's not one time horizon. It's not what geologists call isocronous. So a lot of people don't like this idea because it's just that it's true. It's the emergence of agriculture in the old world, but that occurs at different times in various parts of the planet. All right, so not many supporters for that one. Some of these are kind of nerdy, I have to admit. Like this 5,000 year one. What do you guys think about that? What? Bronze Age. Yeah, that's close actually. I'll have to give you this one because it's so obscure. Some of them are pretty obvious, but next slide. The big increase in methane. I guess that is kind of nerdy, isn't it? It's been pointed out that we can actually measure ancient methane levels, and methane is a trace gas in the atmosphere because it's trapped in ice bubbles. So they can measure it quite precisely over the last 10,000 years, and it shows a big increase about 5,000 years ago. And a lot of people think that's because that's the rise of rice cultivation in China, because that's where most methane comes from, is rice paddies. So people seriously suggest that, I mean, that there's something that's global, and it's all through the atmosphere, and pretty, well, not so easy to measure, but it is global in extent. How about 100 AD? This is kind of a nerdy one, too. Good. Iron actually has to do with metals. Hit the return here. Basically, Roman smelting. The Romans were smelting so much that they polluted the whole planet. These trace metals are all over the place. You can actually measure Roman copper and iron in Greenland ice cores, just carried by the wind. And so they were global polluters. And we're looking for something that's global, some kind of geochemical or biological something that's global in extent. And so people have suggested, it's Roman smelting. Now, 1600 AD, I'm going to come back to in a second. I'll kind of a nerdy one. Let me just put it up. The answer is, it's the collision, ecological collision of the new and the old worlds. I'll explain what I mean by that here in a second, because this is a very interesting idea. And how about the next one? Yeah, I have no idea. I prepared this a while ago, and I can't remember, so maybe you guys can tell me. What's that? Yeah, you're good for you, man. You guys are right on it. I think it's Newcomb and it's a steam engine, right? That's about right. It's in the beginning of kind of the industrial age, but although most people would mark 1850 as the start of what? Industrialization. Let's hit the return. What about 1945? What do you think about that one? Don't put it up. Yeah, you guys, this generation knows about that. Yeah, that's right. So first atom bombs. And I was actually I spent my sabbatical in Japan, and my hotel room was like 150 meters from ground zero. Wow, what a feeling that was to actually see this. But the argument for it being the beginning of the Anthropocene is the introduction of all this radioactivity. What about 1964? It's space, but actually it's the radiation peak in the atmosphere, because the end of the above ground testing, it's when the test ban treaty came in, and when you look at radiation in the atmosphere, it peaks in 63, 64. So it's like this global marker in radiation. Okay, so if you don't like any of that, then hit return. There's another possibility. There's the Anthropocene doubters who don't actually think we've had that much of an impact. I don't happen to belong to that category, but I think there's some people that doubt it. It's a tough question. I don't know. And actually, at the end of the day, everybody, I'm agnostic on this point. I don't know. I actually, in some ways, I don't really care either. I think in the near view, this is a sort of scientific relevance. It's fun to think about. In the longer view, there's no question, irrespective of where we mark the bottom, that we've made our mark on the geologic record. That's the bottom line for me. Let me just focus in on just one of these, though, the 1600 AD one, the ecological collision between the new and the old world. Next slide. Okay, this was presented by Lewis and Maslin. This is a really interesting idea. In 1600, right, so Columbus comes to the New World in 1492, and by 1600, there's a full-on ecologic exchange going on between the new and the old world. And they would argue, next slide, that exchange, for example, corn going to the New World, and bananas and other things going to the, other way around, corn going to the Old World and bananas, did you know this? Actually, they're Old World, and they come to the New World. And it turns out that corn produces pollen, and bananas produce phytoliths. Phytoliths are actually little silica bodies that are produced by plants to defend against grazing and so forth, but there's little silica cysts that in a banana are very diagnostic. And the main point is that corn pollen and banana phytoliths preserve beautifully in the geologic record. And that's another thing you want, right? You want something that preserves well, that, somebody comes along 50 million years from now and they can say, oh, well, there's bananas and corn appear on both these continents, and it's sort of a global event. We're looking for global events. So There's been a lot of discussion about this one. That around 1600, that's the beginning of the Anthropocene. We ought to take a vote on this, but it would be too messy. But anyway, think about it in your minds. It's a fascinating question when it begins. Okay, next slide. So defining the Anthropocene, you can do it on the basis of fossil evidence, like the first, one could argue that, well, why don't we do it just on the basis of the first appearance of humans? It's just simple paleontology, right? First human fossils. What's the problem with that argument? What impact? That's right. But for geologists, you can define boundaries based on the fossil evidence itself, or you can do it based on their impact, like what we call trace fossils, the marks and things they leave behind, like a worm leaving a worm trace, or a dinosaur walking by, or a U of A undergraduate throwing a beer can near my house. I'm well versed in that behavior right there. That trace fossil. I live in the West University area, and but actually all this stuff would qualify as, you could mark a geologic boundary this way. And I'm going to argue at the end of the day that it's the Budweiser can that wins. That's because we're throwing around so many more Budweiser cans than we're leaving behind remains of ourselves. I actually did this calculation. This is pretty nerdy too, but here it comes. Next slide. I actually calculated the massive bone of all the people on the planet. That's that little calculation there on the bottom, and I compared it to the amount of trash that we generate as a species in a given year. Compare the two red numbers, and they're 4 orders of magnitude apart. The point is we generate a lot more trash than we do fossil remains. I would argue that future sentient beings, geologists, whoever they are, when they come up to the outcrop, they're not going to be looking at our physical remains. What they're going to be struck by is the asphalt we left behind. Think of the network of roads across this country and what that would look like in the geologic record. It's going to be the remains of roads and guardrails all over the place. The concrete is going to be all over the place. Roof tiles. Let me show you an example of that. Next slide. So during my sabbatical, I went to Nagasaki. That was fascinating because I actually had a vision of what our future archaeological sites could look like if it all ended in a nuclear blast. And it was what struck me about the rubble at Nagasaki. You can go down and actually look at it. Anybody been there? It's really cool. You go down, yeah, and they actually got it exposed. And I looked at it very carefully. It's mostly roof tiles and some teacups, and there was some eyeglasses and a pair of pliers, but it was mostly roof tiles. Those things are going to last 50, 100 million. They'll last a long time, the geologic record. Those are permanent markers. So I've worked all over the world, and I've taken more and more. I'm taking photographs of trash all over the world. I was just in an island offshore in Cambodia, and got up in the morning, and that's what the beach looked like. And at this resort here, so much trash is coming in off the ocean that they have 2 permanent rakers out there just raking it up so that it doesn't offend all the guests. It's really, there's just so much trash offshore in Southeast Asia. And a lot of that's settling into the seabed, and all that stuff's, a lot of it is going to be durable, and it'll be visible in the geologic record. Go out to the Santa Cruz or Rio Grande floodplain, and it's a city dump out there of old couches and things, and all that stuff's going to get caught up in the geologic record. Even, boy, talk about a remote place, the Atacama Desert. I found a hole out there. Actually, it was full of plastic bottles that had blown across from the nearest city, which was 70 miles away. And they just had bounced across the desert and then got caught in this hole. And so in the middle of nowhere, there's all this trash. And that what's not caught in the hole actually ends up being blown out in the Pacific. So I would argue that ultimately in the distant future, what's going to mark our layer for future people coming by the outcrop is just going to be all this trash. It's not going to be fossil remains. As I said before, it's mostly going to be concrete, roof tiles, asphalt, some metal objects, and probably big geochemical anomalies too, insofar as we've polluted things a lot as well. But I think most of the evidence is going to be physical. Okay, next slide. And so we had to really reconsider, why are we calling it the Anthropocene? It's the Garbocene, man. Or how about the Plasticene? This has actually been suggested. There's so much plastic offshore from Hawaii that it's just covering the coral reefs. It's just everywhere out there. This is an underwater picture there in the middle of a typical coral reef, and look at all the plastic in there. And it's, it's lids and pipes, pellets. A lot of it's in the form of chunks because people build campfires on the beach and it melts all the plastic together and then that washes out to the ocean. But that's going to be a permanent marker. So the Plasticene started, if you want to go run with that one, begins in 1856 when Alexander Parkes makes the first plastic. That's the beginning. It's not the Anthropocene, and it's not anything we named. It's this date. So take your pick. And as I said, I'm agnostic on this. It's just fun to think about it. Next slide. Okay, for the last portion of my talk here, I want to talk about the first human footprint. I have the greatest job in the world, and part of it is I get to camp out a lot, as Aaron mentioned in the introduction. But the other part is I get to travel all over the world. I've always wanted to do this, and I've always been fascinated with the human fossil record. And I have been working out there for about 15 years in Ethiopia, actually documenting the first footprint. The first human trash, actually. And I'll show you some photographs of it. I actually found it, me and another archaeologist. These are students and colleagues in the foreground, and this setting, I know it looks like Benson, Arizona, but it actually isn't. This is so quite similar, actually, when you get there, though. This is the Awash River in central Ethiopia, and this is the area where just up over the horizon is where Lucy came from. You heard of the Lucy fossil, a famous Australopithecine, so it's right in that area. And we found a lot of those kinds of fossils as well. Okay, so I want to show you, actually just walk through a series of slides about fieldwork in Ethiopia and what the first footprint looks like. Okay, first of all, there's the fossil evidence. The fossil evidence for humans, we're rare as hen's teeth. One of the things you realize, there's lots of fossils out there. But most of them, anybody want to guess what the most common fossil that you stumble across out there is? Seashell. No, the ocean isn't here. Think of an animal, land animal. What would be the most common animal? And it's not us. Cows. How about hippos? Hippos and crocodiles, like 90% of the stuff. And what I realized is that we were small players. In our early origins, when you just add up all the bone that's out there, there's all these other animals in a Serengeti type sort of landscape, and then just ever so occasionally, if you set up a camera on a hill and sort of filmed everything 5 million years ago, hippo, crocodile, and then occasionally an elephant, then some antelope would go by, and then warthogs, and then if you were really lucky and it had really stuck with it for maybe a month and watched, you might see a group of humans walk by. So we're rare. But I want to show you when you actually find something, when you find a human remain, it's kind of anticlimactic. Next slide. And our setting is Ethiopia, by the way. And in the Gona and the Hadar project area, that's where Lucy came from. Okay, so you know the physical setting. So next slide. That's it. In all the years I've worked out there, I don't spend my time looking for fossils. I'm not a paleontologist, but I did encounter this one, and it turned out to be the skull cap of a hominid, and it's just sitting on the surface. But I wasn't even sure at first because it was so fragmentary. And but I thought, just in case, I better take I can take some photographs of this. We'll get it back to camp, and they can identify it. Because I'm a geologist. I'm not a paleontologist. The guy I was with, who was an Afar tribesman, I said, here, you hold on to everything. We'll collect the bits. And I thought he was quite a striking guy anyway. And I thought, well, this is kind of a National Geographic moment, so I'll take your photo. So his name was Ibrahim, and I put all the fossils in his hand, and here's the next slide. So there's Ibrahim holding what's the, let's see, what are the bits there? There's the, this part right in here. That's the brow ridge right in here. And it was all kind of a jumble when I picked it up. And we were about 12 miles from camp. And I didn't want to leave it out because I was talking to Ibrahim in Afar, actually. And he was saying, the rain is coming, and the rain is coming. And I agreed. And I said, we got to take it with us. And I didn't have anything to put it in. I don't usually sample. So I just took my socks off. And I put all the fossils down to my socks. And I just nestled it like this for 12 miles, just walking along, We got back to camp, and I got it back, all the pieces back to camp in one piece. And we all stood together, and each of us holding different pieces. Next slide. That's what we got. Isn't that something? So this fossil, it's not published yet. This is about 1.9 million years old. It's an early form of Homo erectus. It's our genus, not our species. But definitely one of our ancestors, a female in her mid-20s, something like that. Relatively small cranial capacity, but just a classic Homo erectus. And it's much more complete than that. We also have the face and all that, but that's just the parts we were holding. Okay, next slide. There's lots of fossils out there. Anybody want to guess up there in the upper? You guys are really good, so I'm pushing you here. Up here, up in that panel right there. What do you think in the northwest corner? It's a weird pattern, isn't it? What do you think of that? So it's pretty big. A mammoth, good. That's right. It's actually not mammoth, but it's an African elephant, Elephas recii, and that's the tooth. It's in profile, and they're really the dime a dozen out there. So many. Down in the southwest corner there, that's it's a fossil pig. It's called Metridia curus. And man, I found the entire skull, and that pig must have been the size of a Volkswagen. I mean, it was really a Volkswagen Bug anyway. But man, everything seemed big back then. And that's one of the molars. That very distinctive pattern is typical of pigs. Up in the northeast corner, that's actually a snake, and it's in a volcanic tuff. So it was killed by a volcanic eruption. And I saw a whole complete snake in there. We also found a hominid in there, which is very interesting, a Homo erectus. So it was kind of a Paleo-Pompeii. And then even perfect, complete eggs, not even crushed. It's unbelievable, huh? Preservation. So lots of cool fossils, but as I pointed out, you find lots of this stuff. I mean, every day I'm picking up stuff like this. But maybe a couple times a field season, you'll find a human fossil. They're just really rare. Next slide. What is not rare out there is the first trash. And another Afar that I worked with out there, a guy named Habib, he's holding, and in the background you can see stone implements. So these are stone tools. They're the earliest types of stone tools. They're called Oldowan choppers, and they're the first trash. This is it. This is the first stuff that, at least trash that, is preserved in the geologic record. And just a comment about Habib. So these are Afar tribesmen, Danakils, and boy, they've been amazing to work with. I get a weird feeling about this, though. I mean, Habib is dead, and so is Ibrahim, and it just reminds me how short life is. In sort of the pre-modern era, he died of some sort of fever, and Ibrahim was killed by the Somalis. And life is short. So, but at least looking forward to meeting some of my surviving friends out there. And boy, they love to go out on long walks with me and look for fossils. So we're on the same page. And they like hanging out with me. In fact, because I like to walk and I don't drink that much water. And in fact, one day I was quite touched by this. One of the Afars pointed to me and he said, "Adu Afar," which means you're a white Afar, which was a rude compliment because these guys are tough. So I'm going to Ethiopia tomorrow. Did I mention that? Yes, I actually am climbing on an airplane and I'll be doing field work. See these scenes right here on Sunday. When you sit down to breakfast, this is where I'll be. So I'm cutting it kind of close here, burning at both ends. So anyway, let me show you the oldest stone tools that have ever been found. Those are the oldest trash. Next slide. It's called the OGS archaeological site, and that's a tarp that's spread across a steep outcrop. And for scale, there's people underneath the tarp doing an excavation. We put the tarp up. This is at 9 degrees north on the equator. It's super hot. And so whenever we do excavation, we cover things up. So it's a big outcrop. The reason we were attracted to this thing is because of that white layer up there. Next slide. That's a volcanic layer, which we dated to 2.5 million years ago. And the stone tools in this archaeological site are clearly below it. So it provides a minimum age for the stone tools. We know they're at least 2.5, and we now know they're about 2.6 million. So those are amongst the oldest, at the time they were the oldest known stone tools, or my point of view, the beginning of the Garbacene is right there. But that doesn't work. It doesn't work because garbage, the Garbacene starts at different places at different times. It doesn't get going in here in the Americas until there's peopling in the Americas, and that's relatively late. So it's not a nice homogeneous or isochronous boundary that would satisfy most geologists. But anyway, I got to see it. I had the privilege to see it. Okay, next slide. And this is a close-up of the world's oldest stone artifacts at the time. And I know it's not nothing particularly write home about, but there they are. Flakes knocked off of a core by one of these early hominids, presumably one of our direct ancestors in the Homo genus. Although we've never found fossils associated with it, we don't actually know who did this. That's a big question, but we assume it's our direct ancestor. Okay, next slide. As you move forward in time, the trash gets more and more abundant. It gradually increases, and the tools become more sophisticated. By 1.5 million years ago, a million years later, they're making what they call Acheulean hand axes. I'm holding one there in my hand, and there's some examples there on the ground, and they're big, sort of lozenge-shaped things, and knocked off with big cores. And to break off and flake rocks that size is extremely difficult. One thing I realized about Homo erectus, and that's the guy who did this, he must have had one hell of an arm, because it takes a lot more strength to make these things than I certainly have. They must have been very, very strong. But a lot of these things, what basically you see in the geologic record out there is more and more stone tools, more trash, and right up to the present, it's just sort of this exponential increase in trash. And I've had the good fortune to see the first steps in that. Okay, I'm going to close my slide by asking you, or my presentation with this last slide, ask you to imagine a Grand Canyon 100 million years from now. And so you come as a tourist and you visit this, and the one thing I feel sure about as a visitor, next slide, that the chief attraction is going to be our layer. And maybe you even get lucky and find the Statue of Liberty sticking out, but more likely something like a Ford truck or a roof tiles or something like that, but something, you'll see it. Okay, thank you very much.
You can answer questions. Okay, just a reminder, both Samantha and I will make our way around the room. I'll give you a chance if you'd like to take a drink of water before you field questions. Are you okay?
I'm good.
Okay, so Samantha's over in that corner. I'll go over here. And just by a show of hands, who would like to, we'll hand you the microphone, hand it back. Oh, first question.
Why do you think the cold-blooded animals like crocodiles survived the KT extinction event?
Good question. Indeed they do, don't they? Funny you should ask that, because people have wondered about that one. One thing they've noticed about crocodiles is they can go very long periods between meals. They can go months, actually. Can you imagine that? And so it's been speculated that that's why they made it. If you can survive basically in the absence of food for months, that would have increased your chances of surviving. And if you're burrowed down in the mud banks, below the surface, as crocodiles will do with a nest, shield you from basically the ground would insulate you from the cold. So people have wondered about that one, and that's the speculation.
Just a second. You pass right.
So from your point of view, is there any hope for the human race?
I'm feeling a little glum right now, actually, on that question. I don't know, what a question. Who knows? There's a big literature out there that basically argues that civilizations are like, they're biological, and they're born, they live, and they die. And it's actually being anticipated by government agencies right now. I worked for many years at Yucca Mountain. This is a roundabout way to answer your question, but I actually think there's a lot of skeptics out there about our long-term survival. I worked for years at Yucca Mountain, and which is, charted, has been slated to be the long-term, high-level nuclear waste storage facility. And in the guidelines, they write it in the guidelines for the scientists working out there. It basically says, don't anticipate we're going to be around. Anticipate that this nuclear waste, when future people come upon it, they'll have no idea what they're looking at because everything would have been forgotten. So there's actually formal governmental structures anticipating in the longer view we're not going to make it. And our rise, this exponential increase in everything we're doing right now is so sudden and it's so meteoric that I just don't see how it's sustainable. I honestly don't. Everything's happening too fast. I'm hopeful, but it makes me wonder.
So hippos and crocodiles live in muddy, wet areas. I would think they'd be more likely to produce fossil evidence than most other creatures.
Just because of the preservation potential. Yeah, you're right. I think there is a bias built into that to some extent. That the areas that are topographically the lowest, it's where the fossils collect. Although it's interesting, we find a lot of hominids actually mixed in with the hippos and crocs. And I think the reason is they're all living close to each other right on the lake edge. Everybody wants water. So they're not that far apart from each other, actually, in terms of the fossil evidence. But I think, point taken, there is this preservation bias that would favor them. But I don't think it explains, I stand by what I said before. The overall pattern is we're extremely rare in the fossil record.
Do you have an explanation for the cause of the ice ages, and how do they figure into these epochs? Yeah,
the cause of the ice ages. Yeah, that's a good question. It's a big question. Witness the fact that the poles of the planet right now are ice covered, and they haven't always been that way. Actually, for most of Earth history, we've been in a greenhouse situation. We've had no ice caps. And we live in, I know this is hard to believe, particularly coming from Tucson, but we live in exceptionally cold times from a geologic perspective because we have ice caps, and that's unusual geologically. How do they come about? It's probably, in the longer view, it's controlled by carbon dioxide levels in the atmosphere, by the level of greenhouse gases. We're witnessing the effects of that right now in our own climate, but there's a lot of natural variation in those levels. And there's various ways to change those CO2 levels in the atmosphere naturally without us even touching the dial. And so the challenge is understanding what those controls are, and I think we only have a partial understanding at this point. But I am convinced that at the end of the day, carbon dioxide is the policeman. It's the thing that is running it, that controls the planetary thermostat. And you raise and level and lower CO2 and temperatures will follow. And it's been quite dramatic. In the Cretaceous, it was a lot warmer than today, and we didn't touch the dial at all. So there's a lot of natural variation going on out there. Yeah. Yes. Yeah. Yeah. So in shorter time scales, superimposed on the fact that the Earth oscillates in and out of this greenhouse and icehouse condition on very long time scales. On short time scales, there's also a lot of wobble in the strength of the glacial periods, of the extent of ice cover. And for example, 20,000 years ago, Canada was under ice. There was no Canada, and a lot of Northern Europe was under ice. And so those shorter term cycles are thought to be controlled also to some extent by carbon dioxide, but possibly affected by changes in the Milankovitch cycles. For those of you who don't know what that refers to, it's just a Serbian astronomer who coined this sort of, or originated this kind of idea that changes in the character of the Earth's wobble control the amount of incoming radiation in the planet, and that occurs in sort of regular cycles. They call them Milankovitch cycles, and that ultimately controls the short-term sort of in and out of strengthening and weakening of the ice house. Right now we're in an ice house, but it's a weak ice house. we're slated to go back into a strong ice house. What if Milankovitch is right? If I could live another 70,000 years, we could really test his hypotheses. But unfortunately, I'm not going to be around. But he predicts that in another 70,000 years, we'll be back into the ice age. Unless we screwed things up too much by then.
Yeah.
In one of your slides where you showed a series of panels where things are increasing.
Yeah, yeah.
Up in the upper right corner, you had a panel on methane.
Yes.
And the methane values there were higher than carbon dioxide.
Yes, that's right. Methane.
And that's a more efficient greenhouse gas than carbon dioxide.
Yes, excellent observation. That's right. There's various flavors of greenhouse gases, and the two big culprits are the famous one, carbon dioxide. But methane is a really potent greenhouse gas, and it's not as abundant as CO2 in the atmosphere, but there's a lot more bang for the buck. And you're right, it's more than doubled. Yeah, more than doubling. Yeah, which is more than the increases in CO2. That's right. So it contributed, the general thinking is it's contributed to some of the warming that's occurred over the last 100 years is that increase in methane. The big question is where it's coming from. And it's not from the backside of cars. It's not from industrialization in cars. It's a reduced gas. And we know some of it's rice paddies, right? But those have been around for a long time. Cows are probably a big contributor. Yeah. Yeah, in the tundra, that's right, actually frozen in. And that's why there's a lot of concern about this permafrost melting and this feedback that the more permafrost you melt, the more methane you release out of these high latitude bogs, because that's where a lot of this methane is made, and then it's gonna warm the atmosphere more. That's right. So people are really watching places like Siberia very closely, because you melt that permafrost and you're going to get release of this very potent greenhouse gas, as you point out.
I've heard that comment about cattle a lot, but why do we think there's more of an issue with cattle than with the hundreds and hundreds of thousands of buffalo that roamed the plains earlier, which they probably exceeded the number of cattle we've got now?
So cattle, I'm sorry, the contents of methane or what? Sorry.
Why do we think that cattle is such a big issue when cattle have merely replaced buffalo, which roamed the plains in huge numbers?
Oh, I see what you're saying. Yeah. Yeah, that's a good point. I wonder how the numbers actually do line up in terms of domesticated cattle and so forth compared to the number of buffalo thought to roam. But if they were relatively equal, then I think point taken that they couldn't have been a big contributor. The disappearance of buffalo would have been compensated for by the replacement by cattle. So, but methane, there's multiple sources, and there's a big debate about where exactly it's being released from. But the general thinking, it's mostly out of frozen soils in high latitudes. Also in boggy and marshy settings at lower latitudes. So animals maybe make some contribution, but it's dwarfed by these other sources. And the fact that we're melting so much permafrost right now, that's the big concern. There's also, incidentally, a lot of methane frozen into the seabed. They refer to them as methane clathrates. And that's another thing that people are watching. Most methane is actually tied up in the seabed. But fortunately, right now, it's frozen down there, mostly.
We have time for a couple more questions if we have them.
First of all, thank you for your presentation. I enjoyed it very much. In listening to it, I'm trying to figure out why apparently geologists are spending so much time trying to figure out when the start date is. I mean, just pick one, Why the agony?
Why the agony? Well, it's like just get a group of scientists in the room, try to get them to agree on anything. Sometimes it's really hard. I don't know. I could hold up my hand and say, okay, it's going to be, you know, case settled. It's going to be the first trash. I found it 2.6 million years ago. And then somebody else is going to stand up and say, no, 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 that's stupid, you know, and lay out the reasons. There's actually no real perfect. You see the problem. I bet if we got everybody to vote in the room here, could we get everybody to agree? There'd be no way. It'd be all over the map. And you're right, it's a scientific question. And geologists don't spend that much time worrying about this. They have other things to work on. But I enjoy it for debate purposes, just sort of thinking about all this in the context of human history. What everybody decides on in the end, I don't really care. It's fine. Yeah.
What do you think the role of plate tectonics and volcanism plays in carbon dioxide levels in the atmosphere and the fluctuations that occur?
Good question. There's no question about that question that it modulates. That most of the CO2 in the atmosphere comes out through volcanoes. When you measure gases coming out of volcanoes, it's mostly water and then secondarily carbon dioxide. And so that's being introduced into the atmosphere, and then, so that's sort of a source, but then there's various places that it's consumed in various different ways. Organic matter, for example, photosynthesis, that consumes that reservoir and somehow keeps the whole thing in balance. So, but you're right that variation in the sort of rate of plate tectonics is going to be a control on carbon dioxide levels in the atmosphere. And so just a little while ago, I was talking about how the Cretaceous was a greenhouse world. What do you imagine rates of volcanism are thought to be during that period? And the high, that's right, exactly right. Seafloor spreading rates, tectonism, everything is elevated in that period. And so there's thought to be a connection. These periods of strong volcanism, seafloor spreading, and losing my earphones here. Sorry about this. That's better. Rapid rates of seafloor spreading seem to correlate with periods of warm climate. And so I think that's the first order. That's why probably the Cretaceous is a greenhouse world. Oh, continents. And continental drift and so forth. Yep, yep. Yes, that's right. In fact, there's a word for that. It happens in cycles. What they'll do is they'll split apart and go across the planet and meet each other on the other side, right? And they call that a Wilson cycle. That was recognized about 25, 30 years ago. And so where in the Wilson cycle are we right now, do you think? About halfway, that's right. And let's see, we split up, the Atlantic opened up starting back in the Cretaceous period, mostly. Mesozoic period, let's say 150 million years ago. And it's been, so the Atlantic is opening up. North America is eventually going to collide with Asia and form a so there's periods where everything's split up and then it all amalgamates into what they call a supercontinent. And the supercontinents come together roughly every 500 million years. So the last supercontinent was, so we're midway through, aren't we? It was about 250 million years ago. And they referred to it as Pangaea. And the one before that, 750 million years ago, was called Rodinia. And so your question is very prescient. That's exactly right. There's these amazing big cycles that occur. Yeah.
Could everybody join with me in thanking Dr. Jay Quade for his talk tonight? And before you go, I just want to make an announcement for next month. Remind you that we do have evaluations out on the table in the foyer. And then those of you that would like to come down and ask Jay some questions, you can make your way down here. Next month on February 15th, Humans and Humidity, How Past Climate May Have Shaped Our Evolutionary History by Dr. Andy Cohen. So thank you again for coming tonight, and feel free to make your way to the front if you'd like to ask some questions.